more stable than the other depending on what's attached. But do you guys see the ring flip?
Yep.
So here's the question I have for you. We started with a colored piece on the axial position. Isn't that right?
Yep.
Where is it after the ring flip?
It became an equatorial.
It became an equatorial. Exactly. Whenever ring flip happens, whenever a cyclohexane ring flips, one chair flips into the other chair. Axial becomes
Equatorial.
and equatorial becomes
Axial.
whenever cyclohexane chairs flip, the axial bonds become equatorial, equatorial bonds become axial. Do you see that?
Yep.
Everybody sees that? Cool. Everyone okay with that?
Yep.
So whenever ring flip happens, for example, so let's start here. Axial, 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 axial.
So this goes down, then this goes up.
Equatorial, equatorial, equatorial,
And this
equatorial,
becomes
equatorial, equatorial.
Equatorial.
So what will happen to the red bonds after the ring flip? This is called the ring flip.
The red becomes equatorial.
Exactly, the reds become equatorial. By the way, this carbon is up, right? Can you tell me, I'm going to call it carbon 1 just so that we can refer to it. Can you tell me in this example that I have on the screen, after the ring flip happened, where did carbon 1 go?
It's on the bottom.
Which one?
Bottom right.
Exactly. When you ring flip, you push this down, push that up. So carbon 1 that was on the top now is at the bottom right there. Exactly. So please notice those relationships there. So the carbon 1 is here. Do you all agree?
Yep.
So what will happen to the red bond and red bond? It will become equatorial. All the red bonds, but here's another important thing to notice. Please notice. The red bond on carbon 1, was it pointed up or was it pointed down?
It was pointed up.
And it's still pointed up.
Pointed
The
in
direction of the point does not change. Whatever was going up stays up. Whatever was going down stays down. It's just that whatever was an axial environment now becomes equatorial and vice versa. So if something were pointed up, then it's still pointed up. And the same thing, the axial on the next carbon, notice, was pointed down. It's still going to be pointed down, but this time it's not axial, it's equatorial. You guys agree?
Yep.
Everybody sees that? Because that's very important. Next axial was up. It's still going to be up, but not axial, equatorial. Next axial was down. It's still down, but equatorial. Next is up. It's still up, but equatorial.
Yep.
And then the last one was down, so it's still down, but it's equatorial. So whichever bond was pointed upwards, it's still upwards. Whichever bond was pointed downwards, it's still pointed downwards, except that equatorial becomes axial, axial becomes equatorial. Same thing here. Let's fill in the fourth bond, starting with C1. The equatorial was pointed down, right?
Yep.
So it becomes axial.
Pointed down.
Exactly. The next equatorial was pointed up. It's still pointed up, but it's axial. Axial. So whenever ring flip happens, whenever cyclohexane chair forms, whenever we say cyclohexane, your brain should tell you chair. That's it. Whenever we look at cyclohexanes in whatever context, in our minds we should see it as a chair, because that's the most stable form cyclohexanes to be in. So whenever a chair cyclohexane undergoes ring flip, here are the things to note. A, axial bonds become equatorial, equatorial bonds become axial. B, whatever was the original direction of a bond, up or down, stays the same. It is still up or down, except axial becomes equatorial, equatorial becomes axial. Is everybody okay with that? Yes? So please, again, practice drawing these because you just get better at these with practice, in my opinion. So just as I said, you're sitting watching TV and the movie is boring, whatever, and then just grab some color pencils and start drawing stuff. Okay? Okay, next thing. Any questions so far, by the way? Cool. Next, what I want you to do is make for me a methyl cyclohexane. Methyl cyclohexane. Please make a model. Methyl cyclohexane.
Not on paper.
No, not on paper. Model.
I was in the
We will also do it on paper.
Done.
Yes.
That's my method.
Can it be like these?
Anything for now.
Can it be?
Has one carbon and three.
But that's, if you know that's methyl. If you think you know that's methyl. Methyl cyclohexane.
Yeah, the gray ones, I mean, the silver ones don't matter, the gray ones are
I think.
You guys good? I mean, how are you going to make a methyl group then, Mark?
I have carbon. I need a carbon. Yeah.
Okay, are you guys with me, guys? Okay, so here's my question. Did you put the methyl group on the axial position or did you put it on the equatorial position? Okay, how many of you put it on the axial position? Show your hands, please. The rest of you put it on the equatorial positions? Okay, cool, that's fine. What I want you to do is, whichever position you started with, I want you to take your methyl cyclohexane and give it a ring flip. That's not chair.
Okay.
It has to be chair,
I'm sorry,
guys.
this is axial, right?
That's axial, yes.
That's excellent.
So if your methyl was equatorial, great. Give it a ring flip. If your methyl was axial, great. Give it a ring flip. It doesn't matter. You guys done?
Yeah, almost.
So what happened to the methyl? Which position
broke.
did it go into? If you started with axial, it became equatorial. If you started with equatorial, it became
Axial.
right? Because when we ring flip, the designations of those groups change.
And it's not all the way.
Okay. Are you guys with me?
Yep.
So if this is methyl, I'm choosing to start with methyl being equatorial. Do you all agree that's equatorial? And then I'm giving it a ring flip. So whichever carbon was going down is now up. Whichever carbon was up is now going down. What will happen? So this carbon right here, calling it carbon 1, is right there. Do you guys all agree?
Yep.
Okay, so what will happen to the methyl group? Which direction is that pointing? It's axial now. Straight down, axial. Do you guys agree?
Yes.
So the next question that we are going to discuss are both of the, by the way, what's the relationship between these two structures? Are they isomers, conformers, unrelated?
Conformers.
They're conformers. Bond rotation, conformers. Agreed? Are these two conformers equally stable, or is one of them more stable than the other? That's our next point of discussion. So, when you look at your, yeah, please, what? May I borrow that more?
Is the axial be more stable because the methyl is farther out from the rest of the molecule?
Actually, it's not.
Oh.
So, that's what I wanted to point your attention to. Could I borrow 2 of the red pieces? Thank you.
Red? Oh, this
pieces.
one? This is
So guys, when my methyl is in the axial position, there is one unfavorable steric. We call this steric because it's not torsional strain, it's steric strain. It's still about space. It's still about crowding. It is still about electron clouds not having enough space to exist. So there is a very unfavorable interaction that exists when we have a group in the axial position, and that is relative to the one I'm holding where the methyl is. There are 2 of these axial positions. Their cloud interacts with this electron cloud. So I just wanted to point your attention to, let me show it to you here on the board, which ones am I referring to? There are two axial positions on the third carbon. If this is carbon 1, 2, 3, so this axial position, and 1, 2, 3 on the other side as well. The electron cloud here and the electron cloud here interacts unfavorably with the electron cloud there. This is called 1,3 diaxial. It's a steric interaction. By the way, if you ever hear the term sterics, it's implying crowdedness. And when atoms or groups come too close, that causes steric interaction. Steric is not good because it's making things too crowded. They don't have space. That's unfavorable. So the axial position is less stable than the equatorial position because axial positions have these what we call 1,3 diaxial interactions in space, which makes that position not be as favorable. Equatorial position does not have that issue at all. When a group is in the equatorial position, there are no such, they're all on the outside, so they do not have these unfavorable interactions that they have to deal with. So point number 1, please make a note. Axial position is less stable than the equatorial position. You guys with me? Everybody okay? So which of these two conformers, in your opinion, will be favored? Right? So at equilibrium, of course, they are ring flipping and becoming each other constantly, but at equilibrium, which of these conformers will exist more? The equilibrium will favor that. Make sense, everybody?
Yep.
Cool. So I'm just making up a number here. I have zero clue what it's supposed to be, and that's really not important. Let's say at equilibrium for methyl cyclohexane, the mixture is, let's say 60% and 40%. Because the equatorial position is more stable than the axial positions. With me? Everybody? What do you think will happen instead if I had isopropyl cyclohexane? So notice I'm changing the group CH3 versus CH, CH3, CH3. Can it also ring flip? Absolutely, right? When it ring flips, which position does the isopropyl group go to? It becomes axial, because it was equatorial, it becomes axial, right? Which is more stable, the first conformer or the second conformer? First conformer, second conformer, more stable. Equatorial or axial? No, exactly. Don't get tricked. Equatorial versus axial, which is more stable?
Axial.
Always.
Oh.
Always equatorial more stable than axial.
Oh, less
Period.
stable, sorry.
Good. So the equilibrium, of course, will favor the equatorial. But here's what I want to ask you. And here's where you have to think. Let's say if this mixture was 60-40, what would you expect this mixture to be? Would there be more of equatorial compared to there, or less of equatorial compared to there, or the same distribution?
More.
Why more?
I think it's more because there's more electron clouds. Like there's farther.
Why is there more electron? Yep,
Because
elaborate.
There's more atoms sticking out, which means more
Bigger.
interaction.
Exactly. Was that a mic drop?
Yeah, a little bit. Yeah.
Exactly. Sterics is all about size. If the group or atom is bigger, their electron clouds are bigger. If the group or atom are bigger, their electron clouds are bigger, they need more space. Isn't that right? So, does isopropyl group need more space, or does methyl group need more space?
Isopropyl.
Because it's bigger. So exactly. So again, hypothetical numbers here. So because isopropyl is bigger than methyl, this is maybe more favored even than the other. Am I right? Everybody? The most space consuming R group, one of the most, I shouldn't say the most, but one of the most space consuming R group is T-butyl. It's pretty bulky, pretty large. Takes up a lot of space because it has CH and then it has 3 CH3s. Of course, when it ring flips, the T-butyl goes where? In this example, the way I've drawn it,
Down.
it
to the
goes
right.
axial. Now the T-butyl group is so bulky that it's almost, maybe even greater than 99% favors equatorial and very trace amounts of axial because it's so big, it can't be in the axial position. Are you guys following this? So equatorial is more stable than axial, and it has to do with steric interactions, which is about crowdedness, which is about atoms or groups needing space. So the bigger the atom is, the bigger the group is, the more space it needs. So if that atom or group does not want to be in axial position. Are you guys with me? Questions? Yes,
So the
please.
percentages are just favorability?
Those, say that one more time.
Is percentages just favorability?
Exactly, yes, right. If there is 60% at equilibrium, if there's 60% of this, that means this is more favored. Absolutely. Why is it more favored? Because it's more stable. Absolutely. Any other questions?
How do
Okay.
we figure out the percentages?
No, I made up those numbers.
Okay.
No. Those are made up numbers to illustrate the point. The point is that bigger this group is, the more it wants to be in equatorial. The smaller group can still tolerate the axial position. The bigger groups, not so. Are we okay, everybody? And yes.
Did it change with like a good amount of heat? Because like the axial has more energy,
So what the heat will do is basically just make this equilibrium go at a faster rate.
Okay, so it won't change it.
Changes kinetics, not thermodynamics.
Yeah. Okay.
Exactly. Okay, let's take it up a notch. Ready? Ready? I want you to make for me a model of 1,2-dimethyl cyclohexane.
Yes. Yes, sir.
And I wonder
Okay. Two.
how many
Okay.
1,2-dimethyl cyclohexane are there?
You can destroy it.
1,2-dimethyl cyclohexane. That means you're putting 2 methyls on adjacent positions on the chair. Right? Yes? That's not methyl, that's ethyl.
Oh, that's right.
Ready? Please think about it and tell me. How many 1,2-dimethyl cyclohexanes are there? What are those two? Amayas, I see you saying 2. And I'm not talking about conformers. But go ahead. What's the difference? So Amayas is saying there are 2, 1, 2. Can I borrow yours, please?
Is that?
That's, well, but it has to be chair. You have to make sure it's
right.
chair. Okay, so, can I borrow your, yes, can I borrow your, it's not chair, this is boat. Has to be chair, otherwise it doesn't work. Chair. Okay. So notice guys here, these two models, 2 methyls, is this pointing up or down, the one I'm holding? How about this one, the one I'm holding, is that pointed up or down? So if both methyls are pointed up, versus here, is this up or down?
Up.
Oh, that's still up. Ugh. Okay, fine.
2 ups.
Is this up or down?
Down.
Are they the same? Can you take the one that has both methyls up and rotate the bonds, no breaking bonds, no cheating. Can you rotate bonds and make it into this web? One is up, the other is down. So what are they then? They are isomers. Exactly. There are two 1,2-dimethyl cyclohexane. What kind of isomers are they? Are they structural isomers or stereoisomers? Stereoisomers. They are cis and trans isomer. So can you make for me cis 1,2-dimethyl cyclohexane and trans
Okay, I'm lost.
1,2-dimethyl cyclohexane? So, what does cis mean, guys? Same what?
Same position.
Same side, not position. Don't get confused there. Same side, same direction. They're pointing in the same direction. Either they're both pointing upwards or they're both pointing downwards. So don't focus on the position.
I made trans.
So if both methyls are pointing either up or down, that will be cis. Okay, so if I put a methyl here in the equatorial position, will that be going up or down? Equatorial on this carbon, right? So then, in order for it to be cis, what position should the methyl on the next carbon needs to be? Which position is that? Is it equatorial or axial?
Axial.
This is going up. This is also going up. That's cis.
Okay. How
You
would
guys
I,
seeing that?
how would I represent it here? I'm not sure.
What do you mean, how will you represent? It is cis right now.
That's what I thought, but I wasn't sure.
It's up, it's up.
Okay.
It is up and up. It doesn't have to be up and up. It just have to be on the same side, pointed in the same side. Maybe you decided, no, I want to point this one downward. Okay. So then what would be that? Or this. It doesn't, by the way, 1, 2 can be on any side. Okay, let's do it here. So if one of my methyl is pointed down, that's the axial position, what would it have to be here?
Trans.
No, we are still doing cis.
It would be up.
Equator or
It will be up or down?
up.
Down. And what is that? Equatorial or axial? Equatorial. Exactly. That's cis. So cis simply means they're, the two groups you're thinking of are pointing in the same direction. Are you all seeing it? Everybody okay? Give it a ring flip, please. Let's give it a ring flip. What does that do? Remember, ring flip, whichever carbon was up goes down, whichever carbon was down goes up.
Okay,
So where is this carbon of mine? That was down first, so where is it now?
up.
Up. So what happens to the axial bond? And this was pointed downward, remember, please notice.
Axial.
Right?
Axial.
It becomes, axial becomes,
Equatorial. Still.
but it still has to be pointed
Still pointed downwards.
down. Equatorial but down. And that is also pointed downwards, but it is equatorial, so what happens to the equatorial? But it's still pointed down. It's still cis, isn't it? Down, 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 cis. Everybody seeing that? Yes? So when ring, another point to highlight and remember, when ring flip happens, cis stays cis, trans stays trans. When ring flip happens, you're not changing the isomers. Okay, now I want to ask you another question with this example. Ready? Which do you think is more stable conformer of the two? Let's evaluate. What position is this? Equatorial or axial?
Equatorial.
What is that? So it is an equatorial axial combination, right? What about here? Equatorial, axial. So it is also an equatorial axial combination. Which do you think is more stable? Equal. There was one equatorial, one axial in both of them. So they're equally stable. There's really no difference in their stabilities. You guys with me? At equilibrium, there will be 50% of this and 50% of that because they're equally stable. Everybody with me? Yes? Let's do the same with the trans isomer. Those are isomers of each other. So let's do the same analysis with the trans isomer. So I'm just going to randomly start with one conformer. So if I place one of the methyls, okay, please hear me out, processing. If I want my methyl on this carbon to be pointed downward, can you tell me what position
It would have to be.
would that be?
Equatorial.
Equatorial?
Yeah,
Okay, cool. So if that is going to be equatorial and I want trans, what should be the position of the methyl on C2?
Axial.
Trans.
equatorial.
That's going down, right? So this one should go.
Up.
Yeah.
And is that equatorial or axial?
Equatorial, we need opposite directions.
That's trans. One is going downwards, the other is going upwards. Opposite directions. Give it a ring flip, please. Give it a ring flip. So where is that carbon? Where is my carbon 1?
It's gonna be down and axial.
Equatorial will become axial, absolutely.
Yep.
So where is my carbon 2 now? That one. Right? Or that one, fine. It's just that since I was going clockwise, it's better to just stay clockwise. And then what happens to the bond? Equatorial becomes
Axial.
axis. Everybody okay? But please notice, the bond that was going down is still going down.
Yep.
The bond that was going up is still going up.
Mm-hmm.
You don't change that part. Are you guys with me? Now I want to ask you, which one is more stable?
First one.
This is equatorial, right? What about this one? It's axial. What's more stable? Two equatorials or two axials?
Equatorials.
So at equilibrium, the more stable structure is favored. Everybody agree?
Yeah.
Everyone sees that?
So there's no interference between each of them?
What do you mean by interference?
Well, okay, so interaction, so we have steric interaction between
That's not chair.
it and the hydrogen.
I thought it was.
There is, because but hydrogen is so small. Hydrogen isn't very big atom, it's very small. So the interaction isn't very crucial,
Okay.
but it is there.
All right, but, okay, let's follow this, is that the equatorials, the two side chains, seem to be in each other's way.
On 2D,
And
on 3D not.
whereas in the AA, they're on totally other sides of the molecule.
3D it's not. There is no interaction that's happening that is going to cause, that is as big as the interaction between the two.
Okay.
So when those groups are placed outside of the ring, they have less harmful interactions than if they were placed in the axial positions. Does that answer your question? Okay, cool. Coming back though, are we all okay that this conformer for the trans isomer is more stable than that one?
Yep.
Everyone good?
Yep.
So my next question. Ready? These are the two conformers for the cis isomer. Yeah? These are the two conformers for the trans isomer. Yeah? Which isomer is more stable? Is the cis 1,2-dimethyl cyclohexane more stable or trans 1,2-dimethyl cyclohexane more stable?
Trans.
Why? Why?
Cause, okay, I
No,
might be
no.
wrong.
Okay,
but
what if I said you're right?
I want to say it's because it's more favored for it to be equatorial, so it means it'll happen more often, maybe, right? Whereas that
Don't
one,
say
it's always
happen more
gonna be.
often, because that has nothing to, happen more often implies that there's actually a conversion between cis and trans. There isn't.
Okay.
But you're absolutely right. Trans is the more stable of the two because it is the one that has the most stable conformer. Of all the four conformers that you see here, that isomer is the one that has the most stable conformer.
But doesn't it also have the least? So that's why.
But then the percentages, again, I'm just going to make up numbers. Please don't take my numbers as much. Which one is the predominant conformer? Which one is the predominant conformer for this isomer? EE, right? So if you have 100 molecules making up number, 75 look like this, 25 may look like that. But this is the predominant conformer. Which is the predominant conformer here?
No.
No.
They're both the same. So of the predominant conformers for both isomers, which one is more stable? That becomes the more stable. Make sense? So of course, yes, it does contribute, but that's a fewer proportion. So we're looking at the most important conformer for both isomers and then picking the isomer that has the most stable conformer. We good, everybody?
Mm-hmm.
Yes, sure? Okay, then you tell me if this makes sense. Let's do the same analysis this time, but this time let's do it for 1,3-dimethyl cyclohexane. By the way, sorry, somebody said something. By the way, can you guys pause and please tell me what is the relationship between this compound and that compound? I haven't changed that one. How is cis 1,3-dimethyl cyclohexane related to trans 1,2-dimethyl cyclohexane?
Structural lesson.
They're structural isomers. Do you see that?
Mm-hmm.
Why? Why are they structural isomers?
Same formula.
Same formula, different structures.
Exactly. The atoms are connected differently. Absolutely. Those are structural isomers. But anyways, I'm asking you to do the same stereochemical analysis between these two stereoisomers, cis and trans. Let's do the same. So, could you just give me 1 second? Go ahead, please go ahead. Start with cis and then let's do with trans.
In paper.
Say again?
In paper.
Once you understand the models, you don't always have to make models. Now we understand what's going on, so I'm starting with one chair. Okay, so can someone tell me if I wanted a methyl on this carbon to go down, what position would that be, axial or equatorial?
Equatorial.
And then I want cis, 1, 3, 1, 2, 3. So to be cis, what should be the position of that methyl group?
Down and axial.
Is it axial?
No.
It's 1, 2, 3.
Oh, okay.
Equatorial as well, right? It's down, down. You good?
Yeah.
So it is an EE conformer. Am I right?
Yeah.
Let's give it a ring flip. When you give it a ring flip, equatorial becomes
Axial.
and vice versa. So that goes down and so this is AA. Do you agree? Which conformer is more stable of the two?
The EE.
Let's do the same for trans. Okay, so if I made that equatorial, what should the second methyl be in order to be trans? If that's down,
Pointed up.
we need, and what is that, axial or equatorial?
Axial.
So that's EA. Give it a ring flip. Equatorial becomes axial, down, down, and 1, 2, 3, that's up. Axial will become equatorial, that's EA. And I hope you will agree with me that they're both equally stable. Agreed? Everybody okay so far? Which isomer is more stable this time? Is the cis isomer more stable or the trans isomer more stable?
Cis.
Everybody agrees with that? Why? Because it is the cis isomer that has the most stable conformer of the four, so that is the more stable isomer. Is everyone understanding the analysis here? Yes? The more stable isomer will be the one that has the most stable conformer. Make sense, everybody? So at home, can you do the same analysis for 1,4? So just do the same thing. Cis 1,4-dimethyl cyclohexane, trans 1,4-dimethyl cyclohexane, and figure out which is the more stable isomer of the two. Everybody okay? Yes? Can I borrow that worksheet you were showing me earlier? Actually, I might have it also somewhere. Guys, can I answer any questions here so far? Okay. If we get this, please go ahead and draw for me.
Okay.
The more stable. Oh, okay. Okay, why not? Isomer, please read very carefully, of 1,2-diethyl cyclohexane. So we have to do this analysis before you can come up with the final answer. You have to look, since it said isomer, what are they referring to here?
An isomer that is the
Different.
most stable conformer.
No, okay, fine. What are they really, what are they?
Cis and trans.
Cis and trans, exactly.
Yes, cis and trans.
They're talking about cis and trans. So you have to do this analysis. Cis 1,2-diethyl cyclohexane, what are the two conformers? Trans 1,2-diethyl cyclohexane, what are the two conformers? And then which one has the most stable conformer? Does that make sense? You guys want to do that quickly?
Yeah.
Okay, so for the cis, let's just do the cis one first. If I make this equatorial, it's 1, 2, what should that one be to be cis? Is that going down or up?
Down.
Is this going down or up?
No.
Down? So what should this one be then?
Down.
And that would be what? Equatorial or axial?
Axial.
Right? That's equatorial axial. Equatorial axial, when you give it a ring, and do you have to draw everything? Not really. Not really, if you think about it, right? If it's EA, what happens to E when you ring flip?
It becomes A.
And what happens to A when you do a ring flip?
It becomes E.
So wouldn't that become AE when you
Yeah.
do a ring flip?
Yeah.
Right? Okay, that's cis. What about trans? So in order to be trans, what should be the relative positions of the two ethyls? If this is going down, equatorial, what should the other one be? Equatorial or axial?
Equatorial.
Because that's going up. Absolutely. So that is equatorial, equatorial. Right there is your answer. If the most stable conformation possible is EE, and whichever isomer can have EE is the more stable isomer. So in this example, that's the more stable isomer. Does that make sense, everybody? Yes? Okay. The next one here on this list is the less stable. Please notice. Conformer. For 3 propyl cyclohexane. So you don't have to do all of that here, just the chairs is okay.
Oh,
You don't have to do
okay.
any of that,
Okay,
just
I
the chair
thought
form.
this said
No, I know, I understand. So the chair is giving us a conformational perspective, so you don't have to draw Newman projections. Okay, so here's the thing, guys. In this kind of question, notice that the groups are different. They're not the same. So far we've seen groups be the same, right? So here's my question. Which of these two groups, methyl or propyl, is bigger?
Propyl's bigger.
You all agree?
Yeah.
So what position for the more stable, okay, for the more stable conformer, what position would the bigger group want to be in?
Equatorial.
Equatorial.
Right?
Yeah.
For the more stable, bigger group wants to be in the equatorial position. Isn't that right? But they asked us for the less stable. So for the less stable,
We need our.
what position will you put the bigger group in?
Axial.
So, let's start with that. Let's start with making a chair and putting the propyl, the bigger group. Always start with the bigger group. That's the one that decides because that's the one that needs most space. So because we want the less stable conformer, I'm going to put my propyl group 1, 2, 3 in the axial position. That's fixed. Now you get to decide, okay, we also have a methyl in the 1 position. If this is 3, then 1 position, and it has to be cis. So 3, 2, 1. Let's say that's carbon 1. So what would methyl have to be, equatorial or axial, for it to be cis with respect to that?
Mm-hmm.
Do you see the thought process that's going on here?
Mm-hmm.
Everybody okay? So, does that make sense now?
Yeah.
Perfect. I think all will be fine. Cool. What if there are more than 2 groups on the cyclohexane? Then what? Let me draw something. Okay, no. Okay, so I'm drawing this tri-substituted cyclohexane, 3 groups on it. And I need you to draw for me the most stable conformer for this molecule. Conform means I'm just asking for, we can't change what's going up or down, that has to stay the same. But you get to decide what's equatorial and axial, right? So, my suggestion, whenever you have a question like this, start with the biggest group. Biggest group. Which of the 3 groups, in your opinion, in this case, is the biggest?
The isopropyl?
There's no isopropyl.
Oh, the T-butyl.
T-butyl, absolutely.
T-butyl.
So, to be most stable, which position would the biggest group want to be? Equatorial. Start with that. So let's say I'm starting with it and I'm putting it in the equatorial position. That's fixed. Now analyze the relative orientations of the others relative to the T-butyl and arrange them where they need to be. So let's start with methyl. Relative to T-butyl, what is the relationship between these 2 groups? Are they cis or trans?
Trans.
Right?
Trans.
Actually, can I change something? Sorry. Could I just noticed I did something that's not quite right. Sorry about that. Here's what I just noticed that I didn't do correctly. That's a wedge. So wedge is coming towards you, right? So generally speaking, wedge would want to be up. Generally speaking. So that's the part I didn't do properly. Okay. Now that's fixed. It is equatorial, it's fixed. Let's go to the 1, 2, 3 position. 1, 2, 3. So what position should the methyl group be put in for these two to be opposite each other? Should the methyl be axial here or equatorial here?
Axial.
Because that's going up, this is going down. And then next carbon, ethyl group. So what position should I put the ethyl group in for the stereochemistries to match? Equatorial, are you sure? Equatorial is going down. Do we want it down? No. These two have to be opposite each other. If that's going to be going down, ethyl has to be going up. That's axial. So fix the biggest first, then arrange the others around based on, is it the same side, is it the opposite side, so on and so forth.
So, okay, so ignoring the structure on the left, if we're just given that, we can't tell if it's wedges in.
Exactly.
But if we're drawing it,
Perfect.
we
You can't.
usually.
Again, to be honest, you're absolutely right. If you were given this and you need to draw something like this and you ended up drawing technically it's correct. Technically it's correct because these do not give us wedges dashes. That's why I said typically we do that. That's not a rule. Not a rule at all. Wedges and dashes are more specific about coming out towards you or going away from you and those kind of things. That information we don't get from here. Make sense? Yes?
So the methyl on the bottom, could that go on the angle above?
This one?
Yes.
Yeah, absolutely. Then you're counting counterclockwise or clockwise, whatever, that doesn't matter. Absolutely. But even if it went here, it will still be axial, right? Yeah, absolutely. No problem. Everybody okay?
Yep.
Cool. Then here you go. Let's make it really fun. And please draw for me the least stable structure. Conformer. 4. The least stable structure for this molecule, conformer for this molecule. So which group will you start with? Yes? Which group will you start with?
The propyl group,
Because
more carbons.
it's bigger. It's all
bigger.
about the surface area, size.
It's bigger in
surface,
size.
right. Not weight, it's about the surface area. Absolutely. So, which position would you want to put it in?
Axial.
Because,
Least stable.
exactly, right? Because that's the one it doesn't want. Okay, so if I put it axial going down, put it like that. Now that's fixed. Relative to this position, we can assign others. So I'm just going to go clockwise, just cause. You can go anti-clockwise, that's totally fine. Okay, so let's go to this methyl. what position should I put it in? Equatorial or axial for these to be opposite orientations? If this is axial, what should this be?
Equatorial.
Careful, not necessarily.
Axial.
If this is going down, this is going up, right?
Axial going up.
And it's on the next one, so it's axial going up. Everybody okay?
Yeah.
Let's go to the next one. Which position should I put the hydroxyl group, the alcohol group, on the next carbon? This is going up.
Down.
What does this want to be?
Down.
So what position would that be on the next carbon? Axial or equatorial? Going down. That's why we really need to know our axials and equatorials. Everybody okay? So that's done. Let's go to the next one, ethyl. It's also going down. So what position would that be on the next carbon, equatorial or axial?
Equatorial.
And then finally the methyl on that fifth carbon, it is going up opposite to the ethyl. So what would that be on the next carbon, equatorial or axial going up?
Equatorial.
Equatorial as well. I'm not very good at drawing this part, just FYI. You can even draw it this way. That's totally fine. But please notice what we are doing here. We are picking the biggest group and fixing its position. If the question is asking for most stable, put the biggest in equatorial position. If the question is asking for least stable, put the biggest group in the axial position. And then go around and assign other groups appropriate positions based on, are they on the same side or are they on opposite sides? Everybody okay? Yes, please.
So the last two are equatorial.
In this case, yeah.
Because they're just on the other side.
See, these are on the same side. I'm going by, oh, that's opposite. Oh, these are opposite. Oh, these are the same. These are opposite. Do you see that, Carrie? Yes? So starting with the biggest. If that's going down, these two are opposite. So then this has to go up. On this carbon, that's axial. We good? Now, if that's going up, this is going down because these are opposite. Going down. Well, on that carbon, that's axial going down. So that's how we just went around and placed everything.
And the last two.
So if this is going down, that's also going down.
But it's equatorial.
That's equatorial, going down on that carbon. Exactly, because axial goes up on this carbon. Remember? Yeah? And then of course, these are opposite. So if this is going down, this has to go up. And on that next carbon, axial goes down, so that has to be equatorial. With me?
Yeah.
Everybody? Yes? Just to remind everyone, if you need an explanation, or no, not an explanation, a reminder. Axial is up, carbon up, axial down, axial up, axial down, axial up, axial down. Those are the axial positions. And then the equatorial, if that's axial is up, equatorial is downwards, upwards, downwards, upwards, downwards, upwards, or you can draw it this way too if you're good at it. I'm not very good at it. So, does that make sense, Karen? Practice, please practice. The point that is important to keep in mind, wedges and dashes are not telling us axial equatorial. Wedges and dashes just don't tell us whether this has to be equatorial or axial. What is telling us if it's axial or equatorial is, okay, if this is on C2 and I want it going up, well, it has to be axial because on C2, up is axial, equatorial is down. So that's what's helping us figure it out. The natural glucose structure. Glucose is one of the sugars, one of the carbohydrates. Again, this is more of a biochemical context, but sugars in nature adopt a cyclic structure, which, too much detail, there are two different kinds of ring structures carbohydrates adopt in nature. One is called a pyranose form, which is a 6-membered ring like this. Just like cyclohexane, even though that's an oxygen, doesn't matter. It still takes on a chair form. And all carbohydrates have multiple OH groups. Again, that's more of biochemistry, but those are all related topics. That's a wedge. Can you draw for me the most stable conformer of the natural form of D-glucose? That's a planar structure. I need you to draw for me the most stable conformer. So if you see 6-membered ring, not benzene, benzene has pi bonds. If you see a 6-membered ring with no pi bonds, you should draw a chair, automatically, a chair. Whether one of those is an oxygen or nitrogen, does not matter. So since it's a 6-membered ring, a chair. But one of those is an oxygen. Isn't that right?
Yep,
How many bonds does oxygen want to make?
2 bonds.
So are there any axial equatorials on those?
No.
No, because it's already making 2 bonds. Of course, yes, there are 2 lone pairs, of course, and yeah, sure, they'll be in those positions, but who cares? But axial equatorials, carbons have axial equatorials. So here's your equatorial, 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 same thing, nothing changes, guys, equatorial. Here are your axials, axial, 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 axial. Oxygen doesn't have, because it only wants to make 2 bonds. We good? Everybody? Okay, so with that in mind, let's start putting in those groups. So, starting with carbon 1, where should I put the OH? Should I put it on equatorial position or axial position?
Equatorial?
Equatorial? Okay, the next one?
Axial?
The next one?
Equatorial.
Next one?
Axial?
Next one?
Equatorial?
Doesn't change, it's the same thing. Guys, do we all understand? Everybody okay? Yes? I think, let me confirm, I think this is end of chapter 4. Yeah. Any questions for me? No? Okay, let's start chapter 5.
Yep.
No, don't groan. Who's groaning?
Yay.
I said yay and a
Oh,
groaning
okay,
tone.
sure. Yeah, yeah. Okay, I need to find something as an introduction to chapter 5.
Like the same direction. These are all gonna be, it doesn't tell you. Wedges and dashes do not
It's
tell
also
you.
sad to like leave the familiar
They just
stuff.
tell
Now
you
I know
if you're going
everything